Henry Louis Le Chatelier was a French chemist, and he explored chemical equilibria, one of the first to do so. And as such, he has his name on a principle called Le Chatelier's principle. And this says that if we disturb a chemical equilibrium, it will try to establish equilibrium. So let's explore this principle using an example. And here I have some N2O3 gas equilibria with NO gas and NO2 gas. And it just so happens that this reaction is endothermic at 40.5 kilojoules per mole for its delta H. Now, what would happen if we have an equilibrium mixture and we suddenly add more N2O3 into the flask? Well, if we do that, then if we think back to our reaction quotient, if we were already at equilibrium and we add more of this in, then there will be too much of it in the flask. So we'll have to use some of this N2O3 up and make more products. So if we were to add some of this in, the reaction will say, I didn't want any more of that. I was already at equilibrium, and it will work to shift it into products to get rid of the extra reactant and reestablish equilibrium. Now, what would happen if we added more NO2? Well, if we did, then we would have too many products. Now, we only have to add more NO2. We don't have to add more NO in order for this reaction to shift back towards reactants. Because, again, the reaction quotient will be too large and we'll have to shift some of both of these over and make more N2O3. Now, this can be a useful principle because say we wanted to remove all of the NO gas from the container or try to get rid of most of it. Well, if we were to artificially add a lot more NO2 into the flask, then we could use up almost all of the NO, and then we'd be left with largely just N2O3 and NO2 remaining in the flask. So that is one of the uses of this principle. Now, if we are able to add reactants or products into the flask, certainly we could try to remove some. So if there was some way that we could just selectively remove the N2O3 out of the flask, then there would not be enough of it to be at equilibrium if we started at equilibrium. So we pull some of this out, well, the reaction will use up some of the NO2 and some of the NO and make more reactants. So shift towards this way. So it always tries to re-establish where it was. Equilibrium reactions do not like to change. They like to stay the same at equilibrium. Similarly, if we were to remove the NO gas out of the reaction, then we would use up some of this product or some of this reactant N2O3 and make more NO and more NO2. And so, in fact, chemists typically would use this principle to make more products. Say we have something that we actually want to produce, but it's in equilibrium. Well, if we take products out, even just one of the products, then we'll make more of all of the products. And that can be a useful thing to do. All right, what would happen then if we have an equilibrium among all of these gases and we suddenly increase the volume of the container? what does it do? Well, we could figure out what happens by calculating the change in the concentration and then putting those numbers back into Q and then determine which direction the equilibrium would go. And that's certainly a useful thing, but there's an easier way to determine what would happen. I like to think of it just as the equilibrium likes to maintain the same conditions as it started at. And one of those conditions could be pressure. It likes to maintain the same pressure. Now, this isn't the real reason why it would shift one way or the other, but it will always give you the correct answer, and it's a quick way to determine which way an equilibrium would shift. So, if I were to increase the volume of the container that all of these were in, what would happen is that the pressure would go down. And we don't like to change things in equilibrium. So what would end up happening is we look at this and we say, how could we try to get the pressure back up to where it was before? Well, I have 1 mole of gas over here, and I have 2 moles of gas over there. So if I were to take some of this N2O3 and transform it into NO and NO2, then I could raise the pressure back up some, and by making more molecules of gas, that would increase the pressure inside the container. And that's exactly what happens. Not for that reason, but the way to measure that, or how you're determining that, does always give you the correct answer without having to go back through and do a lot of math to figure out what was changing with Q and all of those other parameters. Now we have one more thing that we could do to disturb the equilibrium, and that is we could change the temperature of the reaction. So what if we took this reaction and lowered the temperature? What would happen to the equilibrium? Well, we have some thermodynamic data right here. We know that this reaction is endothermic, so it requires heat for the reaction to go forward. So, while this is not actually what's happening, one of the things that you can do is just write heat on the side of the reaction that it is, right? So since it's endothermic, I'm going to write it on the reactant side because it takes heat to make the reaction go. If this was a negative number over here, I would have written heat over in the product side because it would be generating heat. But this reaction requires heat. And then I can say treat heat just like any other substance in the reaction. So you'll notice that heat is effectively a reactant. This reaction requires heat to go. So if I were to decrease the temperature, that's the same as removing heat from this side. And the net effect of removing something on the reactant side is that we will make more reactants. So some of these two compounds will combine and make this one if we cool the reaction down. Now, conversely, if we heated this up, we would be supplying a reactant in, and that would shift the reaction towards the products. Now, again, just like the explanation for what happens when we change the volume of the container or reduce the pressure, what's actually happening is the value of the equilibrium constant is changing. In fact, the only thing that changes the value of the equilibrium constant is changing the temperature. So, but we can predict what kind of change that would be, whether it would shift to products or reactants, just qualitatively, and that can be a useful thing for when, if I want to kind of estimate, should I have more products or should I have more reactants? What's happening when I change the temperature without having to do a lot of math to figure that out. So that is Le Chatelier's principle. And again, it's really just about trying to maintain equilibrium and not change the conditions that it's under.